Hello, hello, hello. Good afternoon, good evening, good morning, good day, wherever you are in the world. And welcome to the stream for Freaky Physics. For today we have a video lesson. We have CJ coming up today. However, at this moment he's still not in the classroom. So, oh, there he is. He just came in. Hold on, let me fix my camera angle. There. Hi, CJ.
I'm Mr. Dennis.
Right. Okay. How's everything today?
Tiring. Very
Yeah,
tiring.
you mentioned that you had military training, or what's that about?
Alright, it was. So we gotta go like ROTC. Like they took
Mm-hmm.
us out to a camp
Right?
for like 4 days, and it's like
Ooh.
38, 40 degrees during the daytime,
Ah, that's hot. Okay.
and at nighttime it's like 28, 29, which is it felt like 24.
Uh-huh.
Probably because it was really hot, but
Mm-hmm.
then it was cooler compared to what it was during the day.
Right.
So there was no AC at all. It was
Right.
just suffering for 4 days. Yeah.
I see. Well, that's
So
kind of interesting because we
I'm still
actually
recovering.
okay. That's so okay. I guess we're just gonna have to relax a bit today. Well, not too much. We've already done the practice sessions last time, right?
Mhm.
So for today, I was planning to just discuss with you how, basically how global warming works, right?
Sure.
Okay. Uh, okay. Here's the deal about this particular topic before we continue. It's it's conceptual. Yeah, there are equations in this topic, but it's mostly conceptual. Okay.
Mhm.
Uh, right. Hold on. Let me just share the Jamboard here with you. Today's the 3rd. Okay, let's share the Jamboard, and then we start. Anyway, while I'm doing this, I just remembered, since you did say ROTC for military training, right? We used to have that in
Mhm.
the Philippines back when I was still a student.
Oh, why did it end?
Uh, a lot of people complained that it's useless, and the
That's
government
true.
kind of listened. But for me, the way I see it, it actually has a purpose. If
Yeah, it does.
Yeah, but if it's about the military training, yeah, I don't really see the point. But the point for me was it kind of gets you, learning about how to discipline yourself, how to,
Yeah.
yeah. But yeah, there are other things you could do. So anyway, before we start, one last question. I see here in our calendar that we have 2 sessions. So are we doing one or two today? Just to be clear, because I could move the other one
I
if.
prefer I prefer one
Okay,
hour.
I could move the other one for now. I'll move it right now to like at 8 o'clock. Then I'll move
Thursday.
it later. So for now, I'll move it to 8 o'clock
Okay.
just to make it easier. Yeah.
Mhm.
But on Thursday, okay, I'll reschedule that. I think I'll just look for an empty time slot to move that in later. Yeah.
Mhm. Also, I say I'm still recovering because they kept waking us up at 4 a.m.
Uh
and
huh.
like our day started at 4 a.m. and our day ended at 11 p.m.
Ah.
or midnight.
So that's what.
Yeah.
What time do you get? How many hours of sleep do you get? Assuming you go to sleep right away. That's like
Uh,
5 hours of sleep.
yeah, yeah. For
Yeah.
3 days straight. Yeah. And we couldn't wear casual clothes.
Oh well, at least you have
How
that.
was that?
Yeah, when we were doing that, we would actually have our own military style uniforms, and we had to be
Yeah,
in those
yeah.
uniforms.
At all times, right?
Right. Okay.
Uh,
Right. So let's move on. So let's continue now. Let's hold on. I'll just change. I'll just display the board. Is that it? Yep, that's it. All right. So here's the deal with global warming. So again, I usually call this the global warming lesson because essentially that's what it's about. Okay. But in this case, IB doesn't call it global warming. It calls it heat exchange.
Mhm.
Okay. Okay, so again, this is heat exchange, right? Okay. Now, there are three main things that happened here. Okay, if this were the Earth, okay,
Mhm.
and then we have to put in the atmosphere here. Okay, three things happen. We have energy coming in, energy in. Okay, and then there are two bits of energy out. Okay, so we're gonna have two arrows for that. So energy out. Okay, and then the other one I'm going to just say this energy reflected. Okay. And then the fourth one, let me redo that. Energy reflected. Okay.
Mhm.
And then the fourth one, so there are four main things, is that we're gonna do like this arrow going out and back into the earth. So this is energy returns. Okay. Now, we'll get into the details of each of these particular things, but this is the one thing we need to learn or we need to know about how the earth gets warm. Okay. Uh all right. So for the first one, energy in, the important thing here that we need to there are two things that come out. So for energy in, it would either be absorbed, okay? So it will either be absorbed or reflected. Okay. Now when we say absorbed, we're gonna have to use the concept. So the relevant concept here is black body radiation. Black body. Okay. When we have reflection, the relevant concept here is albedo. Okay. Energy out, this particular bit, the relevant concept is also black body. Okay. Now this reflected bit is basically this, right? Okay. And this particular bit, the energy returned, the main concept here is the greenhouse effect. Okay. So, all right. So we got all these ideas, and these all work together to what's this? To keep the Earth whatever the temperature it's at right now. Okay. So we will start with this bit. We will start with this bit. Energy in. Okay. So what happens here when the energy comes from the sun, right?
Oh.
Okay. Energy in. Okay. Okay. Now, let's discuss this in terms of what we have kind of learned in astrophysics. So this is the sun. And then we know that the Earth is a tiny object here. This is the Earth. The scale is inappropriate because if this were in a proper scale, the Earth would be around this big in a proper scale. Okay. The distance between the sun and the Earth is around 150 million kilometers. That's the distance there. Okay. So the idea here, let's kind of go into astrophysics. Okay. In astrophysics, you recall this idea of luminosity, right? Luminosity versus brightness, right?
Yeah.
Okay. Do you remember the difference between these two?
Luminosity. Ooh. I know it's not like I don't know. When I see luminosity, it looks like a reddish thingy, but
Mm-hmm.
I don't know what it means.
Okay. So, okay, luminosity is all about the total power output of the sun or the star. Total power output. Okay. So again, the total power output of the star will be the luminosity, and then the brightness is the um this is intensity. This is another word for it. Intensity, and this is equal to power per unit area. Okay. Now, for us here in this context, we will not be using the words luminosity and brightness. We will be using the terms power output and intensity. Okay. So with this in mind, okay, I'm gonna go look at a particular value in the data booklet. There's something in the okay, somebody's in the stream. VAT10. We're not actually calculating much. We're just going through the concepts. Okay, so we'll do the calculations later. So that's for the guy who's on stream. That's VAT10. Okay. All right. So the idea here is, let's go back to drawing the sun and the earth here. Okay. I gotta look for a particular value here. But before we do that, I'm gonna ask you, given that the distance here, is 150, all right, let's just do that in meters. That's gonna be 1.50 times 10 to the something meters. Million is 6, 7, 8, 11. That's gonna be 10 to the 11 meters. Okay. Now, what I want you to imagine first is that there's a sphere around the sun where the earth is. So it's exactly the same concept we used again in astrophysics. There's this sphere, right? Sphere around the sun. Okay. So the first thing I'm gonna ask you is, what is the area of that sphere? Okay, we want the Earth to be right at the end or right at the surface of that sphere. How do you remember the formulas for that, for the area of a sphere?
Pi r squared.
Pi r squared, correct. And our r is pi times r squared, and this is our r, right? Okay. So, all right, so let's just do that calculation straight away. It's gonna be 1.5 exponent 11. Then you square that. 10 times pi. So that's gonna give you a total area of 70 point, let's just say 7. How many is this? 3, 6, 9, 12, 15, 18, 21, 22. So 7.07 times 10 to the 22. Square meters. Okay. All right. Now, power. Okay, what I'm looking right now is the power output of the sun. I'm looking for that value online because I have no idea. Okay, so the luminosity of the sun. So the power out. So I'm just gonna say the luminosity of the sun here. This is approximately 3.7 times 10 to the sorry, not 3.7, 3.8. 3.8 times 10 to the 26 watts. Okay, so the next question is, what is the intensity of solar radiation on that sphere? Okay. So, okay, can you calculate that real quick? Just put that in a calculator. So again, I'm just gonna copy the area and the luminosities given. Okay, so again, this is the area. And then
You want
the,
me to do what?
okay, so hold on, let me just copy the value again. 3.8 times 10 to the 26. Okay, so we have the luminosity and we have the area. So this luminosity again is the power output, right? Okay, and then I just want to put this here that intensity is equal to power output over area. Okay, so what's the intensity of the solar radiation incident on that sphere around the Earth? Sphere where the Earth is. Okay, so there. Okay, so again, since you're a bit tired, I don't want to rack your brain too much, so I'm just gonna show you this right away. Yeah, so this is gonna be equal to, we're just gonna put that value in 3.8 times 10 to the 26 watts, right? And divide that by 7.07 times 10 to the 22 square meters, and that is gonna give us how much? Let's put that in the calculator.
So, is this like the intensity of the energy from the sun, like intensity of the radiation?
That's
Like,
correct. That's
okay.
correct. So basically, this is the intensity of the radiation that we receive on Earth, more or less. Okay, so let's put that in the calculator. So we have that. So the times 3.8 exponent 26. That's gonna give us approximately 5,400. I'm just gonna use an approximate value here because we don't need this exact value. Okay, so 5,400 watts per square meter. Now, if you think about this, this is pretty intense. It's pretty bright, which is what you would experience at high noon. Okay, so anyway, so this is the average power that the Earth receives when that the Earth receives from the sun on the day side, right? Okay, hold on, I gotta find something. Where's my data booklet? Just to make it easier to continue. Physics data booklet. Okay, so while I'm pulling up the data booklet, so okay, never mind, it's here. Okay, all right, so in the data booklet, it's not opening, it's a bit slow. Let me redo that. Okay, here we go. It's faster that way. All right, so I'm looking up a value on the data booklet. Where is that? It's not here. All right, it's not actually on the data booklet, so it's fine. Okay, so we'll just skip that because it's not on the booklet. So the idea here is this is the intensity. So, whoops. This is the intensity that we get. And that's how much. So you can think of this as the Earth. So that 5,000 so that 5,400 watts per square meter, this is the intensity on the sphere right? Not on the Earth itself, on the sphere around the sun. Now, what does this, why do we have to kind of note this here? Because if you think about this, if this were the sun, and this is the Earth, right? That sphere is huge. Sphere is much larger than the Earth, right?
Mhm.
So, then the Earth, so much so that the Earth kind of looks like a, so, and this scale, this looks like a disc, right?
Yeah.
Okay, so this is why whenever we are doing problems in IB, when it comes to incident radiation, you have to, so this means that the incident radiation lands on a spherical Earth. Not spherical, lands on a circular Earth, not a spherical Earth. Okay.
Mhm.
Okay. So in other words, the area of the Earth here, so the area of the Earth should be equal to just pi times the radius of the Earth squared. Okay. In this particular bit, there's a slightly more complex version of the explanation here, involving angles and everything. But for SL, since it will suffice that we know this. We'll just say that the Earth is approximately a disk at this scale. Okay. All right. So, okay. So let's put this here. Earth absorbs radiation as a disk. Okay. As a disk. Now, I'm gonna write here now the second part of it, that Earth radiates that energy. Radiates energy as a sphere. Okay. So again, Earth absorbs radiation as a disk and it releases energy as a sphere. The reason for that is because the Earth rotates, and so eventually the surface of the Earth gets heated up, right? So eventually when it heats up, it's going to release that energy sooner or later. Okay, so that's the first part. So again, I'll just draw that here. Sun into disk. Earth has a disk, okay? Okay. Now the second part here is, this is the Earth now. And the Earth is going to radiate all that heat like that. And it's gonna do it no matter what, whether the sun is there or not. Right? So that's why.
Oh, really?
Yeah. Because I just have to ask you something first. Maybe just to kind of get the idea across. As long as something is not at absolute zero, it's got some heat in it. So that's the key idea. And absolute zero Kelvin, that's essentially an impossible temperature to reach, right?
Oh, okay.
Right. So what would happen is, as long as something is above 0 kelvins, it's going to radiate energy. But we will take a look at that particular concept further later on. Okay. So far, but okay, is this clear so far? The Earth absorbs radiation as a disk, but releases it as a sphere. Okay.
Why a disc?
Again, it's a disk. Simply there are two reasons for it. The first one is this. The sphere is much larger than the Earth. Let me highlight that. So again, that sphere around the sun is much larger than the Earth. That the Earth's surface is basically, presenting a disk to the sun.
Okay.
Okay. Now the other part of it, there's a second part to it. It's not usually discussed, but the second part to it is it's kind of like, how do I, okay, I think I better draw that real quick. I'll erase this one. So if that's the Earth, okay, and that's the solar radiation coming into the Earth, this is, okay, the surface of the Earth at this point is like that, but the surface of the Earth here is somewhat like that, right? And then the surface of the Earth here, where this light rays incident is like here. So what's gonna happen? Those angles are gonna allow some of the light to be reflected. Okay, and in those reflections, you don't really absorb as much. So same thing here. So with the overall effect, actually, let's just, okay, hold on. Let's just even assume that the radiation is absorbed. Those angles kind of make, okay. So here, it's gonna be something like that. You see what's happening? For the same area, you actually absorb more light in here than here because of the angles that are made. So the effect,
Yeah.
the hemisphere's area, the hemisphere absorbs energy as a disk, as if it were a disk.
Yeah, I can see that.
Okay, but all right, so anyway, so the absorption part done. Okay, so oh sorry, that's the energy from the sun at the moment, right? So let's go now into the absorption bit. So incident radiation. Now, for this part, we're not gonna assume that the Earth, we're not gonna draw the Earth as a sphere anymore. We're gonna draw the Earth basically as we normally do, as the ground. So this is the Earth. Okay, so let's say that the radiation here comes in like that. Now, I'm gonna make this even easier for you to understand why we have to take a look at what the albedo is. Okay, the Earth is not a uniform object, right? Some of the Earth, let's say that this part is a desert, okay, and this part is let's just say grassland, and then this part is ocean, and then this part is ice cap, right? So we know that a desert is mostly sand, so it's kind of light colored. Okay, so what will happen to this incident, to these incident rays here from the sun? So as they go onto the surface of this desert, you don't have to give me a number, but you just have to tell me this. Will it be mostly absorbed, mostly reflected, a bit absorbed, or a little bit of both?
Oh, I think desert reflects it.
Okay, mostly reflected, right?
Yes.
Mostly reflected.
Is that wrong?
Yeah, it is correct. It's mostly reflected. It's just that it's so good at absorbing whatever it can absorb that it gets really hot there, right?
Yeah.
So what happens here? Mostly reflected, a lot of it goes back up, right? But some of this goes into the ground, right? Okay. How about on grasslands? Grasslands are typically dark.
Absorbed.
So mostly,
but it feels cooler than sand.
Yeah, the reason for that is because of the presence of water mostly.
Yeah.
Okay, but most of it is absorbed. So let's put that mostly absorbed. Right? Okay. How about the next one? Ocean, what do you think?
I think absorbed.
Mostly absorbed as well. Because it's dark, right? Even though it's mostly water there, the fact that it's liquid water, it's dark when seen from outer space, so it's mostly absorbed, right?
Hmm.
But how about the ice
Ice
caps?
cap reflect, like fully reflect.
Almost fully reflect, right? So let's write that. Almost fully reflected.
What's something that like fully reflects um
Uh,
radiation?
Nothing. There's no such thing as a perfect reflector. Okay.
Mm.
Even in the context of ideal objects, we have no such thing as an ideal reflector. So
Mm.
close to ideal. I'll just say close to ideal, right? Reflected. Okay. Right. So these concepts here of whether it absorbs or reflects the radiation, this is what albedo is. Okay. Okay.
Mm.
All right. So far concepts are relatively easy, right? So what is albedo? Let's now define it.
How reflective something is.
Okay.
How well it reflects.
Right, it is. There's something missing, but yes, that's the key idea. Okay.
How well an object reflects radiation.
Also still incomplete, but again, correct idea.
Oh.
The one thing that's missing is you need to compare it to something. So compared
Oh.
to what? So this is reflected radiation as compared to what?
Absorbed.
No. What are the two things we're looking at? It's only incident and reflected, right?
Yeah.
So the thing here is gonna be incident radiation.
What is incident?
Okay,
Oh, does incident radiation mean like the radiation that like
comes in.
gets on the land?
Yes.
Yeah.
Which again, if you think about this goes into topic 4, specifically with refraction and reflection, right? Because we call that ray coming in as the incident ray. It's the same idea. Okay, so this is the definition of albedo, and it's okay. So if okay, let's not do the if. So this means that the albedo can have a value that's gonna be between 0 and 1. We don't normally say albedos in terms of percentages. We actually say it in terms of the decimal. Okay, so 1 would be a perfect refractor. Okay, and 0 would be the perfect absorber, right? Okay, so this is the idea here. So the earth. So one last thing before we move on to the next particular concept here is that the earth has an albedo of average albedo. Okay, average albedo of 0.4. Okay, so that means it absorbs around 60% of the radiation incident on it. Okay, or better yet, it reflects 40% of what's incident on it. Okay, so again, albedo is not about how much it's absorbing, it's just how much it's reflecting. Okay, all right, so questions before we move to the next topic, the next concept here. Do you have any?
No, I don't.
None. All right, so this
Like.
okay, so far clear.
Wait,
Yeah,
wait.
go ahead.
Sorry, I have something. There's albedo, and then there's also how well something absorbs
Yes,
something.
and yeah, we have to go back to that diagram here, to the very first
Wait,
diagram
what's
we have.
that term called?
Okay, we're gonna have to look into the concept of the black body here.
Oh,
Okay,
black body radiation.
black body radiation. Okay. Okay. So
I thought it was like permittivity or something, like emissivity.
emissivity, yes. Okay.
Permittivity. Okay.
The idea here is emissivity. Okay, so let's kind of go back into black body radiation again. Okay. Now, we know, I think you've done some experiments before wherein you kind of like have different colored objects and then you expose them to some sort of heat source like the sun or maybe what's this, an incandescent light bulb, and see how the different surfaces would react, right? But basically we know that black objects, right, black objects absorb radiation very well. Okay, so so in this case, because if a black object will absorb radiation very well, think about it this way: because of conservation of energy, if they absorb radiation, what happens in the process? The black object gains energy, right? So as it does, now where does that energy go?
Where does it go?
Okay, the energy of the object increases, and here's the key bit about it. This means it turns to heat. This is absorbed as heat, so therefore the object's temperature rises. Okay, which again makes sense because that's what you do when you wear a black shirt under the sun. The shirt gets really hot really fast, right? Compare that to when you're wearing a cool shirt. You feel much hotter in a black shirt, right?
Yeah.
Okay. Now, have you ever tried this as well?
With a plastic bag and a magnifying glass, like a trash bag.
Yeah. But here's another thing I want to ask you, because you may have experienced it, not necessarily as an experiment, but have you ever done the opposite wherein you wear a white and a black shirt in the cold?
Well, I've never been in a cold place, so.
Yeah, good point.
Yeah.
Okay. Well, the idea here is the reverse is also true. I'll just write it here. So black
Do you
objects
feel warmer wearing black in the cold?
Actually, no, you would feel cooler. Why? Because black objects, I'm just gonna go straight to the point here. Black objects also radiate heat better.
Oh.
Radiate heat faster. Okay, so in both these cases, the black object will be faster, whether it's absorbing it or radiating the heat. Okay, so with that in mind, that means just imagine this first. Imagine if you had a black body. So let's now define what a black body is. I'm not even gonna say what a perfect black body is, but basically a black body by definition is perfect absorber of electromagnetic radiation. It doesn't have to be light. It can be any kinds of electromagnetic magnetic radiation. Perfect absorber of what's this? Perfect absorber of electromagnetic radiation. Okay. So what's gonna happen is, let's say that I'm gonna cut this thing into two regions, region A and region B. Okay. Now let's just say that region A, there's a lot of radiation incident on it. Doesn't matter what kind of electromagnetic radiation at this point, just there's a lot, right? Okay, let's turn that to red. So what happens? All of this would be absorbed. right? And in the process, does what? The absorbed radiation heats up the black body, right?
Yeah, it does.
So hence its temperature rises. So its temperature rises. Okay. All right. So at the beginning, when when the Earth is absorbing, think about it. This is exactly how the Earth is set up. This is the sun, right? This is the Earth. So this is the day side, right? And this is the night side. Again, that's exactly how the Earth works. It's got two sides wherein it's absorbing radiation. And then in B, because here it's kind of warm, it will emit radiation here. So this is the important part about black bodies. Now, the emitting still happens on the day side. So it just so happens that the sun is gonna be more gonna add more energy to the day side, that it becomes hotter than the night side. Okay, so our focus here for black body is this the emitting of radiation. Now the data booklet actually has a formula for this. Okay, there are two formulas. CCC family, good evening from YouTube, hello. Okay, so which one's gonna be important here? It's this. Okay, I'm gonna write the I'm gonna put the formula right here, and I'm gonna discuss what these mean. You've seen this in the astrophysics section as well. You've seen a similar formula, right? So this P here is the power radiated. Okay, T is the temperature of the body. Okay. A here is the surface area where it's happening. Okay, so temperature. The A is area. Sigma is what's called the Stefan-Boltzmann constant. We've discussed this further as well, before rather. So basically, this is a constant, right? And this E is the you mentioned this word earlier today. This is the emissivity. Okay. Now the emissivity, just like the albedo, the emissivity has a range, and that's gonna vary between 0 and 1. Okay. The emissivity basically is let's define it on the next page. Emissivity. Okay, this is defined as the amount of radiation that a body will actually radiate. Okay, this is still a comparison compared to a perfect black body. Okay, so this is the definition of the emissivity. So if I write that as a formula, the emissivity is equal to radiation emitted over maximum possible radiation emitted.
Oh, there's a maximum possible radiation emitted, a perfect black body.
So, yeah. So if the emissivity is 1, then that means it releases all the energy it could.
Yeah.
Okay.
And that is a black body.
So the emissivity equals 1. Okay. This is a perfect black body.
Yeah.
Okay.
Well, so Earth could be a black body because it emits.
we assume that all bodies at this point is a black body, just to make calculations easier.
Is a moon a black body?
The moon, in this case, we can consider the moon as a black body.
Okay.
Okay, again, in calculations, but in reality, not even the only black body in the universe is the universe. Everything else is not exactly a black body. Yeah. So of course, when the emissivity is 0, it doesn't radiate. No radiation, right? And then for any other value, emissivity is greater than 0 but less than 1, we call that a gray body. So it's not quite black. We call this a white body, by the way. Yeah. So everything else in between, we call that a gray body. Because it's somewhere between black and white. Right? Okay. So for, so the first part, again, radiation coming in and being reflected first. How much is reflected? That's albedo. And then whatever's left over, how much will it absorb? That's black body. And then how much will it emit? It's also black body, but this is again, that's it, okay? And then the third one, before we go into the third one, I want to just finalize for now something about the Earth, okay? So let's go back to the Earth. So we'll do now emissivity. Albedo and emissivity at work. Okay. Emissivity at work. Okay. So this is where you will see why we need the greenhouse effect. But let's kind of do this first. If this were the Earth, okay, and then let's say that the albedo, let's use the average albedo of 0.4. That includes the clouds, the ice caps, everything else, right? And then let's say that the emissivity equals 1. And then we know that the solar radiation is incident on the Earth, and this has an intensity of approximately 5,400 watts per square meter. Right? And I'll make this easy. I'm not going to ask you to calculate this now. I'll just actually look for the value. What's the surface area of the Earth?
Surface area?
Uh-huh.
How do you find surface area?
That's going to be 4 pi r squared. Pi r squared, rather, right?
4 pi r? Oh. Pi r squared is area, right?
But that's for a flat circle. But how about for a sphere? 4 pi r. 4 pi
surface
squared.
area.
Yeah, surface area.
Oh.
Well, we don't have to calculate that. I'm just gonna look for that. That's going to be I want to convert this to meters. Hold on. 1,000 times 1,000 is 1,000,000. So 12. That's gonna be 510 times 10 to the 12 square meters. Trillion is 12. Yeah. So let's kind of put that in here. So 5.10 times 10 to the 14 square meters. Okay. So with this, let's kind of look about let's just look at this real quick, okay? Now let's assume that the temperature of the Earth is constant. Why do you assume this? Because if it in this assumption, that means energy in equals energy out, or not energy. Let's use the word power. But it's the same idea, right? Power in equals power out, right? So we're gonna look now at the two formulas. What's the power in? So power in would be equal to the intensity times the area, right? And then power out, we'll use the black body. We'll use the black body formula. Power out would be emissivity would be 1 sigma at to the 4. Okay, so E sigma a t to the 4, right? So the question is, what is t? Okay, so for us to answer that, we're just gonna have to equate power in equals power out, right? Okay, so in this case, remember what we discussed before. Power in, this must be a disk, right? And this must be a sphere. So okay, we're gonna equate the two now. So after this, we can end. Okay, so if we equate the two, what do we get? So I times area, that's gonna be in fact, we don't actually need the area. I'm just gonna say that this is gonna be pi r squared because disk, right? That's gonna be equal to emissivity sigma the area, then t to the 4. Because this now is a sphere, we're gonna have to use 4 pi r squared. Let's cancel stuff out already. The pi and the r squared cancel out, right? And then let's move everything to that side. So we get t to the 4. That's gonna be equal to the intensity over emissivity, black body, that's 1. Let's put the values in now. This is gonna be 5,400 over emissivity is 1. Sigma has a value. Let me just check the data booklet for that. I forgot, but I think that's 5.67 times 10 to the 8. Yep, minus 8. So 5.67 times 10 to the minus 8. Okay. So I'm not gonna show the rest of the calculation. I'll just finish it right here. So t to the 4 would be 5,400 divided by 5.67 exponent negative 8. That's t to the 4, right? Then from here, we take a double square root to find t. So take the square root of that and take the square root of that again. That's gonna give us 555 Kelvin. Okay, hold on. Did I do this right? Because I got a value that's way too big. All right, let me check later, but that's the idea. So whenever you're being asked to find the temperature of the earth after certain, oh, that's what I forgot that the emissivity is not 1. Oops. Okay, sorry, it's not the emissivity. I forgot to put into the account here the albedo. So I'm gonna have to add here 0.4, right? Okay, so let's do that again. 5,400 divided by 0.4 times 5.67 exponent negative 8. Take a double square root. Made it even bigger. Alright, I'll have to find out where I went wrong, but basically that's the idea here. Okay. By the way, this temperature should be in Kelvin, not degrees Celsius. Okay.
Okay.
Alright. So I guess we'll end it here first for now, CJ. I'll see where we went wrong, but go ahead, ask.
So disk, you say Earth absorbs radiation as a disk because the sun shoots only one side of the Earth.
Yes.
Okay. But then when it emits from the whole body.
Yes. And then the curvature of the Earth kinda has the effect of making that half a sphere into a disk. Okay, so that's why we use a disk. All right. Any other question? No. All right then. So I guess okay, we'll end it here. Again, for today we're only going through the concepts and a bit of the calculations. But next meeting I will add I will add the greenhouse effect, and then we'll go through some problems. Okay.
Mhm.
All right. So if that's it, then do you have any questions before we end? Any other questions?
Um, this topic seems very similar to topic 7.
It is. Topic 7. Which part?
Like the equation where it's something about like t to the power 4 as well.
Oh, yo, that's not topic 7. That's astrophysics. That's the option. Yes.
Oh, okay, then it's
Yes.
very similar to astrophysics.
There's a reason for it because the reason is we also do the same assumption that stars are black bodies.
Mhm.
Okay, so that's why the formulas. It's not actually just similar. We're using these same equations just on a different context.
Okay.
All right.
Yeah, oh, then it's like electricity and the GMM over R squared.
Yeah, a little bit
It's like the
that.
Q1, Q2.
Mm-hmm.
Okay.
Yeah. So it's the same. It's in the same idea as well.
Yeah,
All right.
but different context.
Different contexts. Which is why I love
Okay.
teaching this after astrophysics as well, because it makes more sense. All right.
It
So
does, yeah.
all right. So okay. So if that's it, then I guess we can end the lesson for
Wait.
today. Oh, go ahead.
Question: is the TOK essay graded by the teacher or externally graded?
TOK. I think it's externally graded.
Oh,
But of
so I
course,
won't know until I finish my exams.
yeah. Normally, I know that the the internal assessments, all IAs, and the extended essay are internally marked, but moderated.
EE is externally.
Sorry, EE
Oh,
is
moderated externally.
yeah, moderated externally, but TOK, from what I understand, it's really externally assessed as well.
Okay.
All right, but I'm not 100% sure on that. I gotta double check. All right. Anything else?
That's it.
All right, so we'll end it here. So CJ, I'll see you again on Thursday, and I'll reschedule the second hour today to some other free time. Yeah.
Thank you.
All right. Okay. I'll see you next time. Bye bye now.
See you. Bye.
Right. So that's the end of the lesson. So the stream, if you're still there, I think you're still there. Hold on. Let me get to that. Okay. So for those who are still on the stream, thank you for staying. Hope you learned something. So basically, let me recap that quickly. So again, the Earth absorbs energy from the sun. And the sun makes it warm. But the process of getting warm means if it's warm, it's gonna radiate heat away. And the amount of radiation the amount of energy it radiates is gonna be dependent on its temperature. So the sun sending all that energy in, and the Earth radiating the energy. Once the amount of radiation going out equals the energy going in, the Earth should have more or less a constant temperature. If it radiates more heat than it emits, than it takes in, then it should get colder. And then if it radiates less heat than it takes in, it should get warmer. So that's a key idea. And that's the attempt here. So I'll just show that again. That was the attempt here. I think I made a mistake in some value. I think it's probably the albedo of the Earth. Okay. But either way, at this point, I'll see where I went wrong. We'll go through that on our next lesson with CJ. Again, I hope you learned something though. Even though the calculation itself was wrong, it's still the correct idea. Okay, so that's what we did here. Power in equals power out because the temperature's constant. Okay, so with that, we'll end it here. So before we do, don't forget to like, share, and subscribe to any of the following social media platforms, whether it's YouTube, Facebook, TikTok, Instagram, or you can follow us on Twitch for the stream. Again, stream happens on Facebook, YouTube, and Twitch. Announcements happen on Facebook, TikTok, and Instagram. No announcement for this week though, because I'll be honest with you, I'm a bit busy this week. and the week, the past week as well, and the week following, and the week after that. So basically, for a month, I'm quite busy with something. So right now, I just go on the lesson. You'll be notified. Hopefully, you get notified and you jump in. Okay. If you don't jump in, that's fine. All right. So with this, again, don't forget to like, share, and subscribe. So for now, this is Freaky Physics. Stay freaky, everyone. Bye bye now.